In this session, we will discuss about circuit basics, and we'll look at electronic circuit terminologies and relations between these terminologies, and we'll lay a ground for the rest of working principles in electrical electronics engineering. Okay, the most basic electrical circuit has at least current and voltage as variables. Now, the flow of charge through a circuit element is called current. Now we'll discuss also what a circuit element is and how we define it. But for now, the energy that drives this flow of charges is called voltage. So at least the most basic circuit has these two variables as a minimum. So let's talk about current. Current is fundamentally defined as the rate of charge flow, and we need to pay attention that it's just not flow of charge but the rate at which charges flow. We designate current using letter I. So current is the rate of flow of charges, so charge Q per unit time T. From this we can see that charge Q is the product of these two variables, current and time, I times T. Okay, as we said, we're looking at the change in the charge flow per unit time, dq by dt. Of course, charge is measured in coulombs, current is measured in amps, and time is measured in seconds. Let's take example. Now assume this circuit element has two terminals, terminal A and terminal B, and 5 coulomb of charge flow through A to B every 10 seconds. Okay, this means that 10 seconds are required for 5 coulomb of charge to flow through A to B, according to this example. This scenario could have been different if we had changed other variables, for instance voltage, but we will discuss about that later on. Now calculate the current flow. So what is the current flow? So the current flow, as we have said, is defined as the rate of I is the rate of charge flow per unit time, and in our case that is 5 coulomb per 10 seconds. So this will give you 0.5 amperes. And let's talk about voltage. Voltage is designated by letter V. If you try to separate two charges, the distance then creates a potential difference. Okay, so it means that energy builds as a result of the separation of the charges, and it matters how many charges are there, all right, involved in this separation. So therefore it's the rate of the energy created because of that per unit charge that we call voltage. So voltage V, voltage is therefore the change of energy, is the change of energy per unit charge. Okay, per unit charge. Now we can formulate it as follows. You can say that V, voltage, equals delta energy delta is standing for change here, per charge, or D, again change, energy E per change charge. In similar manner to current, we can also calculate this energy to be equal to voltage times charge. And of course, the unit of energy here is joule, and the unit of voltage is volts, and charge coulomb. All right. Now, so let's look at a similar example here. Example 2. Okay. Now, think about that circuit element. So we still have the same circuit element as an example. If the voltage difference between points A and B is 10 volts between this point and that point, voltage equals 10 volts. And what we are looking at is calculating the amount of energy that's required to actually push through 4 coulombs of charge. So this is voltage difference between points A and B. Now, how much energy is required to move 4 coulombs of charge from A to B? So we require to calculate energy. Think about this relation. But we know that voltage equals change of energy per change in coulomb. So from this, energy equals voltage times charge. So our voltage difference is, the voltage difference is 10 volts times 4 coulombs of charge. So the energy required to push through those 4 coulombs from point A to point B, therefore, is 40 joule. So we looked at the common variables in a circuit element, which are current and voltage. But the discussion of current and voltage also gave rise to electrical energy, which arises from the separation of charges. Now it's worth to discuss a little bit more on this energy. So if we look at the first terminology that comes to mind in the discussion of energy, is the rate of this energy per unit time, which we call power, designated by letter P. So power equals change in this energy that we discussed over unit time. We can calculate energy from this relation as D equals power times time. Now, if we can further investigate the relationship we've just defined here, we said power equals change of energy per change in time. If we can multiply this with the following quantity, dE dt multiplied by dq per dq, multiplying by dq over dq does not change the original meaning or value of your ratio here. Then we can then rearrange this as follows: dE over dq, taking this denominator here, okay, times dq per dt taking that denominator as a denominator on the second fraction. Now what we are saying basically is P equals dE per dQ times dQ per dt. But now we know that from our discussion of voltage, it is the change of energy per unit charge. So we already called this voltage. We also know what this variable is. That's the flow of charges per unit time, which was current. Okay, so we can now see that power equals voltage times current. So that's also one important relation that we need to keep in mind. So let's look at an example here. Now assume that circuit element we discussed earlier. Now let's this time assume that the voltage across this A and B is 5 volt, okay, and a current of 0.55 amps flows through the circuit. Okay, then how much power is associated with this circuit element? Okay, so solution is easy. Now although we have defined power to be the rate of change of energy per unit time, we also know power can be given by the product of voltage times current. So simply we have a voltage of 5 volts times a current of 0.55 amps. Okay, so therefore the power associated with this circuit element for these given variables is 2.75 watt. Okay, so the unit of power is watt. Okay,
I think these videos are brilliant and I'm sure you will like them too. Please like, comment and subscribe, and don't forget to click the notification bell.